Okay, very good. So just one point about logistics. The first tutorial will go up on the below webpage for those of you. Does everybody have access to below webpage? Yeah. The first tutorial will go up on the below webpage for those of you online. I will email out the first tutorial to the Symmetric group. You get a week to work through it. It's largely revision stuff if you want. It's mostly linear algebra, but it's taking all the taking a bunch of stuff that you're already familiar with that you should already be familiar with from linear algebra and translating it into the language of tensors. Okay, so things like cross products, scalar products, etc. can all be translated into this language. That's what you're going to do in the tutorial. Okay, so today I want to talk a little bit more about tensor symmetries. In particular, I want to, having defined what an anti-symmetric tensor was or a skew-symmetric tensor, I want to talk about the symmetric tensor, the symmetric version of that. Which will naturally lead us into what physicists call bosons and fermions, and these are tensors that exhibit respectively symmetric and anti-symmetric properties that we've been talking about. And then I will talk about many fermions and how you code wave function fermions in something called state determinant. So the state determinant is really, if you're doing quantum chemistry, you'll be amazed at how much you can learn from just the state determinant. In fact, much of even modern quantum chemistry is built on using the wave function corresponding to the state determinant. And then finally, we'll talk about epsilon and delta. For the mathematicians in the audience, it's not the epsilon and delta you think about. I want to talk about the Levi beta symbol. There's which is somewhat like a tensor, but not really a tensor, which will lead me to introduce the idea of tensor density. And then I'll talk about something that we're already well familiar with. It's the Kronecker delta. Now we'll think about the Kronecker delta as a tensor of type 1,1. Any questions? Okay, so we've introduced already the idea of skew-symmetric tensors, and I said the skew-symmetric tensor necessitated the introduction of the wedge product between tensors, between vectors in particular, right? So similarly, I can define a symmetric tensor let's call it S, and S will be the tensor with components S, let's say alpha beta, E alpha symmetric product E beta. Again, I'm not, these are vectors, these are basis vectors for the vector space. I'm not using arrows, just imagine that they have arrows. Here, this product is defined to be the symmetric tensor product, so E alpha tensor E beta plus E beta tensor E alpha. So again, let me remind you, the tensor product has the property that it doesn't have any symmetry. So E alpha tensor E beta is not the same as E beta tensor E alpha, but it doesn't necessarily mean that it's plus or minus. Now we're combining them in specific ways to make them either plus or minus. The skew symmetric one came with minus sign, the symmetric one came with a plus sign. So you can see that if I exchange alpha and beta in here, E alpha symmetric product E beta is the same as E beta symmetric product E alpha. Okay. Associatedly, this guy here must satisfy the S alpha beta is the same as S beta alpha. Again, physicists tend to focus on the components, and so they would look at this guy here with two large scale density and call it a symmetric tensor if S alpha beta is the same as beta alpha. Mathematicians tend to focus on the object itself in a basic independent way. Whatever this guy does as a map, that's typically what mathematicians will focus on, and they will be used to interchangeably in this course. Okay. That's just a definition. So I'm not going to go through the properties of this thing here. We've already gone through the properties of skew-symmetric skew-symmetric tensors. The skew-symmetric tensors satisfy some set of properties, which, except for the minus signs floating around everywhere, hold for the symmetric tensors. So I'm not going to double up and tell you about that. You can go over it for yourself and remind yourself of the properties. Where they share properties, they're the same. Where they're different, it's typically a minus sign. Okay, what I do want to tell you is that you can think of both of these operations, skew-symmetric and symmetric tensors, as mappings. Right? We've already defined the mapping by the action of some basis on some other basis. So we can do the same thing here. For example, we can think of them as multilinear forms. So, as an example, E star alpha wedge product E star beta. This would be a basis for a 0-2 skew-symmetric tensor. Acts on, let's say, E mu. E mu, give you delta alpha mu, delta beta mu minus delta alpha mu, delta beta mu. Okay. I need that minus sign there because this must necessarily be a skew-symmetric action on the basis. Right? And that's built in, that's accounted for by this minus sign. Similarly, again, just following on what we've done previously, I can also think of E star alpha wedge E star beta acting on E mu wedge E mu to give me the same thing on the right hand side. Delta alpha mu, delta beta mu minus delta alpha mu, delta beta mu. So, for example, if I have a two-pole, if I have the following two tensors, if I have the following two tensors, A will be a half A mu E star mu, which E star mu, so it's a skew-symmetric 0-2 tensor, and B the half E mu, E mu, which E mu. So this is a skew-symmetric 2-0 tensor, then I can evaluate using those relations what, for example, A does to B, the action of A on B. And this would be order A mu A rho sigma, say, sorry, B rho sigma, E mu E star mu wedge E star mu acting on E rho wedge E sigma. We already know what the action of that is. That's quarter A mu B rho sigma delta mu rho delta mu sigma minus delta mu sigma delta mu rho. And these are just conic deltas, so they just you identify the corresponding thing and you replace it with the mean. That's what they do. So this is just a half A mu B mu. Okay, so you see how that works. These symmetric and anti-symmetric tensors, more specifically symmetric and anti-symmetric tensor spaces, naturally encode the combinatoric properties of and statistics of many indistinguishable polynomials. An application. Nature, as we understand it, is made up of two types of polynomials. Well, please, if you're looking on the thing, let's get that. The two types of polynomials, bosons and fermions. Bosons are matter-carrying particles, and fermions, bosons are force-carrying particles, and fermions are matter particles. Okay, so electron, proton, these are all fermions. The photon, graviton, these are examples of bosons. So, if you were a mathematical physicist or a mathematician, and you didn't really care too much about, what physics these things were coded. Why this is interesting study is because it tells you about the statistics of things that are either symmetric or skew-symmetric. Okay, so what we want to do is study the space of a large number of particles, right? Some n particles. And we care about whether these n particles are fermions or bosons because it turns out that the wave function components of the tensors that describe these guys have different properties depending on whether they're fermions or bosons. And those properties are encoded in precisely the minus sign that comes between skew-symmetric tensors and symmetric tensors. Let me show you how that will work. So to make it a little bit precise, you guys all see the boson. See this. It's better. All right. So, okay. Statement is that skew symmetric and symmetric, and I'm using the right type in a unified way. Tensors naturally encode the statistics of many indistinguishable particles. In many respects, the study of bosons and fermions as indistinguishable particles is a statement about combinatorics. So really, what I'm saying here is that the mathematical properties of these tensors encode combinatorics of many indistinguishable objects. Okay. Okay, so let me make this a little bit more precise. So suppose I have a single particle Hilbert space. So Hilbert space meaning some vector space with a norm that we agreed that we were talking about previously. But suppose I have some single particle Hilbert space. I'm going to call it H. A single particle Hilbert space. With some basis, let's say the basis is EI. Even basis that's I from 1 to n. Then, given this, n bosons, that is to say, if I have some single particle Hilbert space, I'm going to take tensor products of the Hilbert space to describe n particles. Okay, n tensor products will be the Hilbert space for n particles. If those n indistinguishable particles are bosons, then these bosons don't live in the tensor product of n copies of H. They live in the symmetric and symmetrized tensor product of n copies. So n bosons live in sim n of H. This is the symmetrized tensor product of n copies of H. So we always denote it like this. This is the symmetrized version of the wedge tensor product of X. And this symmetrized n product of n copies of H consists of states, which will be tensors that live in this thing, that look like phi. Phi is lowercase phi labeled by I1 to IN, and E1 symmetrized product I1 2 all the way through to IN. Okay. Similarly, if I have n fermions, let's see. These guys live in the anti-symmetrized tensor product. Can you see that? Can you guys see this? The anti-symmetrized tensor product of H. Okay. N copies of H, tensor them together, and then anti-symmetrize. With states that look like psi. Psi is psi I1 to psi IN, U I1, which due to EI N. So this is nothing more than just extending what we've been talking about from a rank 2 tensor to a rank n tensor. Oh, sorry. My definition of these guys came with a factor of 1 over n factorial to avoid overtime. Okay, so again, the anti-symmetrized tensors will have a factor of 1 over n factorial, and the symmetrized ones won't. And the point here is that these tensor components satisfy the following: I1 to some I alpha, to some I beta, to I n is minus what I get if I exchange any of these pairs. So I1 to I beta alpha. And sorry, plus sign. And this guy satisfies the same thing except the minus sign. Tensor components are symmetric for a boson and anti-symmetric for fermion. Any questions?
Factor 2 in the second delta, I didn't see in the
This one.
yeah, the anti-symmetrized what a weight product, which product?
I don't think so, but it's not impossible. No. Okay. So one more thing I need to mention is that sometimes an n fermion wave function like this one can be factorized into a product of n single particle states. The equivalent of what we were talking about when we talked about quantum entanglements, and so you just pull apart the tensor product of some large Hilbert space into factor Hilbert spaces, right? So there's an equivalent statement here, and it goes by the name of the Klucker relations, and I'll tell you about it now. So sometimes we can split factor the n particle wave function into n single particle states, meaning that I can write psi as psi 1 psi 2 wedge psi n. I'm talking about the fermion wave function here. Like that. Which means that at the level of the components, I can write psi 1, phi 1, psi 2, phi 2, all the way to psi n, phi n, e phi 1, raised to yeah. By comparing components in 1 and 2, and I urge you to check this, and the way to do it is to check for lower rank tensors, and then you want to use induction to prove that this is the case. By comparing components, I can see that this guy here, the rank n tensor, psi I1 to n, is nothing but the determinant of psi 1 I1 psi 1 2 all the way through to psi 1 n psi 2 I1 psi 2 I2 through psi 2 n. Please do check that. And again, you can check it any way you want, but given that computing determinants is an NPR problem, check it like that. This object here, the determinant on the right hand side, is called the stated determinant, and it represents a very special set of states in the multi-fermion Hilbert space that are factorizable. Okay, again, it's a very special set of states in the full Hilbert space. But as I alluded to at the beginning of this lecture, if you're a quantum chemist, or most chemists that do anything involving quantum mechanics, pretty much everything you do is built on taking the state of determinant, taking that state as your answer and building everything up turning around the state of determinant. Because everything can be computed exactly, well, not exactly, but variationally with the state of determinant, everything that's pretty much everything that's that quantum chemists do is built around this particular state. So the remarkable thing here is not that quantum chemists are lazy, but how much you can actually learn from this rather special state. For the state of determinant. Okay. So Of course, you know, you should ask the question that we asked for the segregation conditions already, which is if I give you a generic state in the n fermion Hilbert space, what are the constraints on being able to factorize that state? And so there we ask, given a generic state in the test product, how do I know that that state is factorizable into a product of different Hilbert spaces? And we came up with a set of necessary and sufficient conditions called the segregation conditions that told us when say psi I j to do x I y j. Okay, there's an analog in this case on the Fluker relations. Let's say that the state is factorizable if and from a wave function, I mean, static symmetric, anti-symmetric Rankine tensor. And it is a necessary and sufficient condition. If psi I1, I2, all the way through to I n minus 1, J1, psi J2, all the way through to J n plus 1. And then I anti-symmetrize over these indices. 0. This is an instruction that everything, all the indices enclosed inside these square brackets must be anti-symmetrized over. So anti-symmetrized over enclosed indices. So for example, if I write down S alpha beta, then this is S alpha beta minus S beta alpha after a factor of half. The point is that I'm anti-symmetrize all of this. Those square brackets mean precisely that minus. You might also in some texts see round brackets. Those round brackets mean symmetrize over those indices. So you change the minus sign to the plus sign. So having introduced the idea of symmetric and anti-symmetric or skew-symmetric tensors, I want to focus on two particular examples of these classes of tensors that will be quite useful for everything that follows. In particular, you'll exploit some of these properties in your next tutorial. So let me state it so that you guys can actually start looking at the tutorial. I want to talk about two particular tensors. First one is defining the delta symbol. Okay, so defining the delta mu defined as 1 if mu equals mu, 0 otherwise. This is a representation of the identity map. Okay, of the identity matrix. There's ones on the diagonal and zeros off diagonal. The key thing about this thing is that it behaves like a tensor properly. Why is that? Well, under a change of basis, by change of basis, I will always mean the change of basis that we've been talking about, right? What happens to delta? Delta mu nu goes to, let's say, delta prime mu nu. Delta prime mu nu was a, say, mu rho, a inverse mu sigma delta rho sigma. But this guy is just a coordinate chart. This guy is just the delta function, right? So delta function delta. So what it does is it meets this guy and replaces it with a rho. Just a mu rho a inverse rho mu. This is a matrix multiplication of these two objects. A is a matrix representation. A mu nu is the matrix representation of the matrix of the coordinate representation. Yeah, the coordinate representation of the matrix of coordinate transformations. So when I multiply them like this with the row summed over, that just says normal matrix multiplication. And since A is being multiplied with the inverse, the result is the identity. The identity is represented by Kronecker delta, and you can see that Kronecker delta is an invariant under the coordinate transformation. But it also means that it transforms, as you would appreciate, a 1-1 tensor form. I think this is trivial because of Kronecker delta. But you can try the same trick with the Kronecker delta with bulk indices downstairs or bulk indices upstairs, then you find that it doesn't. So it's only the Kronecker delta with one index upstairs and one index downstairs that transforms the tensor. The Kronecker delta with one index upstairs and one index downstairs do not transform the same way. The second object I want to introduce is something called the Differential symbol. I say symbol, even though it's going to look a little bit like a tensor, because it's not a tensor. This is called the V beta symbol. It's defined as follows. So you might come across the nomenclature in the literature as the completely antisymmetric symbol or the permutation symbol. So this object is completely antisymmetric in any pair of its indices, and it's defined as follows. Epsilon, say I1, n is +1 if I1 to IN is an even permutation of 1 to n. It's -1 if I1 to IN is an odd permutation of 1 through n, and it's 0 otherwise. Okay. I'm hoping I'm telling you things that you know already, but in case you don't, just take a little bit of getting used to working with these objects. Some properties of the division symbol are the following. One, it is completely anti-symmetric. What this means is that if I exchange any pair of indices, it negates the object, so it brings in a minus sign. So it's completely anti-symmetric. In other words, so then I1, I alpha, I beta, I n is minus epsilon I1, I beta, I alpha, I n. For any set of for any pair alpha and beta. Consequently, if any two indices are the same, then this object is 0. That's what I mean by the otherwise in here. Okay. So this is going to be important when we come to defining what's called the exterior calculus of manifolds that involves objects called forms. And this is necessarily related to the volume of a manifold. Again, you kind of have seen this before in a very different way. For example, when you did multivariable calculus for the first time, you did a double integral. The integral was dx dy. Okay. There's implicit in that statement a direction of integration. Right? You integrated around some curve on a space in a particular way. You went the other way, and it came with a minus sign. Okay. And the way that was built into the object was in that dx dy. That dx dy, that when you did double integrals, was not actually dx dy, it was hidden in there, dx wedge dy. Right? So the volume in an integral, in a double integral, necessarily has a built-in minus sign that's encoded by this wedge product, or equivalently, this guy here, which counts the volume in some way. In a way that I'll make precise in a little bit. When all the indices of this guy is unequal, then epsilon I1 to IN is equal to minus 1 some number p epsilon 1 to n. Give me 1 second, I just need to connect something before the other part to be. I'll be back in a minute. This number p here is called the parity of the permutation. And what it does is it counts the number of exchanges that you need to make to unjumble up this I1 to IN and organize it as 1 through n. Right, so I start off with some general I1 through to In, and I have to shuffle these indices to make them into 1 through to n. Okay, how many times I have to shuffle that, exchange them in pairs, that's what this number p counts. And this is the parity of permutation. The whole factor minus 1 to p is called the sign of the permutation. So depending on parity, whether the parity is odd or even, I either get a +1 or a -1. This is the sign permutation. So the last point I want to make about this thing for now is that even though it looks like it's a tensor, has some set of indices, change the indices, you change the coordinates, you make some coordinate transformation, you might expect that this guy is a tensor, and certainly not this enough looking, but it's not. And the reason it isn't is the following. So let's epsilon is not a tensor. Under the change of coordinates, epsilon I1 to In goes to say epsilon prime I1 to In is a inverse let's say mu let me do this back my one mu1 to mu n goes to mu1 to mu n. A inverse mu1 all the way through to A inverse mu n epsilon mu1 to mu n. This guy is epsilon mu1 to mu n, A inverse mu1 1 all the way through to A inverse mu n and epsilon mu1 to mu n. Which comes from the fact that this here counts permutations of 1 through to n. So I'm going to leave that as an exercise for you to check and convince yourself that it's true for, let's say, 2 objects, and then by deduction find a number of objects. But this guy here is nothing but the determinant of A inches. This is a statement about how we define determinants and the minus sign that comes in the minor expansion of the determinant. You can again check that you can express the determinant of the matrix in this fashion using the epsilon symbol. I wasn't planning to, but I think it may be a good exercise to do in the tutorial, so I'll add that question to the tutorial. Anyway, the point is that under a change of coordinates, epsilon changes to epsilon prime to not epsilon. It differs from epsilon by the factor of the inverse determinant. This is why epsilon is not a tensor. If it was a tensor, it would transform straight up to epsilon mu. It is, in fact, what's called a tensor density. And like any other density, it differs from the thing itself by a factor of volume somewhere. Okay? These things I will make a little bit more precise when we talk about manifolds, but for the moment, let me just justify its calculation. And the way to do that is to make the following observation. So I already defined one other particular rank 2 factor, 0, 2 tensor. That was a metric tensor. Right? We talked about the metric tensor, the binomial form, the component of the metric tensor was something like G mu downstairs. Okay. So we note that under a coordinate transformation, mu, in fact, I don't care about G mu, I care about the determinant of G mu. The determinant of the metric goes to, let's say, G prime, which is the determinant of V mu prime. G mu we know transforms like a tensor, so this is equal to the determinant of A inverse mu rho, A inverse mu sigma, G rho sigma. The determinant of a product of things is the product of determinants. Each of these guys is the inverse of the determinant of the coordinate range matrices. So this goes like the determinant of A inverse squared times determinant of G, which is G mu, which is denoted by this G. Well, what this means is that the square root of G transforms like the square root of, transforms with a determinant of A inverse. And that in turn means that while epsilon itself does not transform like a tensor, if I multiply epsilon with the square root of G, then it does transform like a tensor. So that's 30 epsilon, mu1 to mu(n). I'm going to define the square root of D, and G being the determinant of G mu. Of 30 epsilon mu1 to mu(n) is a full-on tensor. This guy here is precisely the volume of the manifold that we're talking about. That's why if I take the tensor density and multiply it by the volume, I get something that's transformed like a tensor. Okay. Okay, so I'm going to stop there and I'll make one more statement. Everything that we've been talking about so far, technically, is still just linear algebra. It may be a little bit more advanced linear algebra than we learned in second year, but it is still just linear algebra. We started off with vector spaces. We tensored these vector spaces together to get tensor spaces. Then we talked about symmetrizing these guys and anti-symmetrizing these guys. And we talked about thinking about them as linear maps or multilinear maps, but it's all still linear algebra. Okay? This brings us to the end of the first part of the course, which is this thing that we can do things with, roughly speaking. Okay? And I've built it all on stuff that you ought to know already from linear algebra. Basically, just vectors live in vector spaces. A vector is something that transforms like a vector. Okay? The next part of the course, which is what we'll start next with, is trying to build differential calculus on manifolds. And I found it in two parts. One is, I want to tell you what a manifold is, which is what I'll be talking about next. And then we'll try and touch base with some of these ideas a little bit more as well. And I'll go from defining what a manifold is. Will be more or less rigorous. There are a couple of pathological caveats. Well, caveats to take care of pathology that we don't need to talk about, but I'll mention them in brief. Then I'll talk about tangent spaces and vectors, and in particular vector fields. That's the difference between what we're talking about now and what we're going to be talking about when we do calculus. When we do calculus, we want to know how things change. Everything that we've been talking about here has to do with local things that live in a vector space, things that live in a vector space at a point. Right? So now we're going to learn how to take these vector spaces and patch them together over a bigger region that we're going to call a manifold. It turns out that the patching together is actually crucial to this whole story. Right? There are these things called transition functions which tell you how to go from one patch to the other patch. So we're going to take all of these flat space things that we've been talking about, things that take space in vector spaces, patch them together, not by tensor product, by tensor spaces. We're going to patch them together over a bigger object called a manifold. Then I'll talk about things that you can do with these vector fields over the manifold. Lead derivatives, covariant derivatives, exterior derivatives. That will take us to the end of the next part. And that's the end of differential calculus. And then part 3 of the course will be integral calculus. There, to give you a little bit more equipment to work with, I'm going to have to tell you about things that you can integrate over. An integral is made up of 2 parts, things that you integrate over and things that you integrate. Things that go in the integrand and things that you integrate over. So when you wrote down the integral from a to b of f of x was the thing that you integrated. A to b, the integral from a to b was the thing that you integrated over. So it turns out that the things that you integrate over more generally are called chains, and the things that you integrate are forms. So we will talk about integrating p forms over p chains and the mathematical structures that they build on. All right. Any questions?